Hello class, Professor Anderson here. Let's talk a little bit more about curling and this idea that we have a block that's sliding along on the ice. And let's say that our ice really is frictionless. Okay, if the block is sliding along at velocity v, and there's no change in v, then what we're saying is there must be no net force on this thing. But does that mean there's no force acting on this thing? Are there forces that are acting on that stone? Yeah, Megan, what do you think?
Yes, there are still forces. They just equal out.
Okay, what forces should we draw in our picture?
Normal force going upwards.
Okay.
And then you definitely want gravity, mg, going downwards.
All right, I like that. Everybody agree with that?
Yeah.
Okay. When I draw force pictures, what I really want to do is draw a free body diagram. So let's put that over here. And a free body diagram means the following. I'm going to replace my object with a dot. And now I'm going to identify the forces that are acting on that object. And what we talked about earlier was contact forces versus field forces. Contact forces means two things have to be in contact with each other. So which one of those is clearly a contact force? The normal force or gravity? Yeah, Megan.
Normal force.
Okay, normal force N is a contact force because it has to be in contact with the ice. The ice is pushing back on it, but it has to be in contact with it. Now this is, like we said earlier, really a field force when you get down to it, because you've got atoms in there and molecules and charges, and those things are never really in contact with each other. But what we mean is the surfaces are close enough together that the little electromagnetic forces between all those atoms and molecules can actually push on something else. Okay? The other one is, of course, gravity, and that is a field force, because that doesn't have to be in contact with the earth, right? You could have this thing up higher than the ground and gravity would still pull on it. Just like our ping pong ball, when it's up here, it's not in contact with the ground. It's pulling on the ping pong ball, gravity pulls it down, okay? All right, this is the free body diagram. You don't draw velocities on free body diagrams. You only draw forces. The arrows indicate the direction of the force. The length of the arrow indicates the magnitude. So by drawing these things equal length means same magnitude. Since this block is not jumping up off the ice or falling through the ice, I want to draw the normal force the exact same length as the gravitational force down. Okay? The arrow head, of course, indicates the direction of those things. All right, that is a free body diagram. And when you draw the free body diagram, make sure that you identify all the forces acting on the object. Okay, you don't want to leave any out. And you want to get their length and their orientation roughly correct. It's really going to help you visualize how to handle these force problems. Okay, with that in mind, let's move on and talk about Newton's second law. Hello class, Professor Anderson here. Let's talk about the biggie for Newton, which is Newton's second law. Okay, this is where he really laid down some of the fundamental mathematics that we need to understand the universe around us, really tied in the physics to understanding not only the motion of apples falling from the trees, but the moon in orbit around the earth in orbit around the sun, and so forth. Okay? And this is the following simple statement. Force is equal to mass times acceleration. Okay? We talked about force a couple lectures ago, And people said, well, force causes motion. And what we said was, well, to be strictly correct, force causes acceleration. And we want to be a little bit careful about this statement, because what we said a second ago was, if I'm driving down the road at constant velocity, then the net force on me is 0. And yet we know that there are forces acting on us. So what do we mean by that word net? What we really mean is the summation of all the forces. And we have to take into account the fact that those forces are vectors. Okay, so this is the net force, or the vector sum of all the forces. And if that turns out to be 0, then certainly the acceleration is going to be 0. So in our example of the car driving down the road, let's see if we can think about what those forces are and how we might draw a free body diagram to represent that. Okay, what do you think? Dalal, what's a particular force I should draw here on my car?
What do you mean?
Well, this is our free body diagram. Okay, we know that we're moving at constant velocity, which means the net force has to be 0, but there's got to be some individual forces that are acting on the car. So what is one of those forces?
Speeding forward.
Okay, the forward velocity is not really a force, right? We have to think about other things that are acting on this car that are causing it to drive at that constant velocity. What do you think?
Not sure.
Okay, Ben, what do you think? What should I draw here?
I think gravity is pulling it downwards.
Okay, gravity is acting on the car and it's pulling it downwards, and we know that gravity has a magnitude of mg. Good. What else? Yeah, Megan?
Gravity.
Okay, we just drew
Oh, I'm
gravity.
sorry, not gravity. Normal force. I'm
Normal
sorry, the
force.
opposite.
All right, normal force. Now, everybody happy with my length there? It looks like I could draw it just a little bit longer, right? If gravity is that long, normal force should be about the same length, because we know the car is not bouncing up or down, right? It's staying on the road. Anything else I need here? What's your name over there? Peter, what do you think, Peter? What else should I draw on my free body diagram?
I think you should draw friction,
Friction. Which way should friction be going?
the opposite way that the car is going.
Okay. And how big should I make friction compared to these other things?
Relatively small.
Relatively small. All right, I like that. So let's make friction relatively small. We'll label it with a script lowercase f. All right. And what else? Yeah, Michael, what do you think?
Well, if it's on constant velocity, you should probably like put in like the gas pedal of like putting the acceleration on the car.
Okay. Some sort of force that's driving us forward, and that is due to the gas that we're burning in the car, right, which creates these little mini explosions, cranks the piston, attaches to the crankshaft, moves to the wheels, wheels stick to the road. All of that goes into some forward force, which keeps us moving. Should that be the same length as the friction or bigger than the friction?
The same, because the velocity is constant.
Because the velocity is constant, that had better be the same. That's exactly right. Okay, so a lot of your homework problems is just this, trying to get these pictures correct, trying to get the sizes of those arrows correct, trying to get the orientation of those arrows correct.